Hello everyone, Neural Hands here, and today we're going to look at a new power supply. Currently I have two of these Korad KD3005D power supplies that I bought on Amazon. They're pretty decent. I bought one of them quite a few years ago and was pretty happy with it, so I purchased another one, but this one is completely different than this one. Neither one can do 5 amps. They're a 5 amp 30 volt power supply. One of them can do about 4 without overheating, one can do about 3 without overheating. And when it overheats, it cycles on and off. So these are pretty decent for their price, but I wanted something a little bit better. So I did what everybody does when they want to buy high quality test equipment, which is I went to Alibaba and ordered a power supply. Inside this box should be a 60 volt 30 amp power supply. And I wanted a higher amperage because I'm going to be doing some work with lithium cells and I want to be able to charge it at a higher rate than 5 amps. And I'm doing a 48 volt system, so 30 volt power supplies aren't ideal. You can put them in series, but that's not an ideal situation. So this is supposed to be a 60 volt 20 amp power supply. Let's open it up and see what's inside. Now the first thing I noted was the weight of this power supply. It didn't seem really any heavier than my existing 30 volt 5 amp power supplies, so that's a bad sign. But those are transformer based, and I assume for this sort of output wattage that this one is probably a switcher based architecture, and that would make it a lot lighter, so there's still a chance. It looks like they give you a user manual and a couple of copper rings. They should be good for 20 amps. They're labeled 30 amps on the rings themselves. We'll look at this manual later. And there's the power supply. It feels extremely cheap. Very, very cheap. Now, granted, 20 amp 60 volt lab power supplies are pretty expensive, so I didn't expect a whole lot here, and I really don't expect this to be able to support what it's rated for, but we'll test it and see. So here's what came in the package. We get the actual power supply. We get our user manual with a couple of these crimp rings so you can make your own cables. And I get a power cable. That is not the right power cable. This is supposed to be a 120 volt or 110 volt depending on power supply. So let's take a look at it and see if they sent me the correct variant. On the back here it says, not sure if you can read that, use only with 250 volt fuse, still could be a 120 volt model. Here is the actual model number of the power supply that I purchased. It is a WANPTech KPS 6020D, and here it does say 110 volts, 60 hertz. So I am just going to assume that they sent the wrong cable, and I'm going to use my own cable and just plug this into the unit. There is a open cutout here that is completely empty and missing. There is a model of this, I assume, that has a DB9 or DE9 connector here that you can use some sort of digital input or output. I'm not sure. Here are the screw terminals for the output. These are not captured, so you can put ring terminals on these. They screw all the way off. The bottom is pretty unremarkable, as is the top. And it does seem to have one fairly large fan in it, which is nice. And again, the front of this just screams I am cheap. So we'll have to see how this thing actually works, but sure doesn't feel very nice. Here is the instruction manual that I got with the power supply. It is pretty basic about what you'd expect, what to do when you get it. Basically check and make sure there's no damage. Here is a table of the possible model numbers. You can get any of these different model numbers. I purchased the KPS 6020D, 60 volts, 20 amps. And this is supposed to be able to handle 1200 watts given its size and weight. I highly doubt it. Here is the spec table for this particular model, and it's a generic table for any of the different versions of it. I'm not sure how accurate this is. It's probably not very accurate. Instead of actually checking to see if it meets these specs, I'm just going to see how well the supply actually works. So this manual I'm just going to set aside, and we'll test the actual supply and see how it really works and if this was a good deal or if I got ripped off. There doesn't appear to be any voltage selector switch on this, so this is plugged into the wall, 120 volts. I will plug it into here and see what happens. And then we will turn it on. "61 volts, 21 amps. Okay, let's see how these controls work. Looks like if you turn the encoder too quickly, it doesn't register properly, but that's okay. You're supposed to be able to, there we go, press it and change to a different digit. That seems like it works okay. It's a 20 amp supply, but it goes to 21. That's kind of interesting. So everything there on the front seems to work. This particular power supply has a rather interesting function here. If you turn the output on, this overcurrent protection switch, normally when you have your current set to something, your voltage set to something, it will constant current limit at the current limit that you set, 10 amps here. If you put this in an overcurrent protection mode, as soon as it hits 10 amps, it will shut off the output and go into a hiccup mode. It's not something that I intend to use, but it's just kind of interesting that it has that feature. For the first test, let's simply turn on our power supply and test the output voltage accuracy, the DC output voltage accuracy of it. I simply have the output of this supply connected up through alligator clips to the input of my electronic load. And then I also have my true RMS multimeter here, which I know is fairly accurate. And I can measure this at the output of this power supply, because if I put current through it, these clamps will get the resistance losses of the wire, so it won't quite match up exactly. So we'll use two different meters here for this test. And here I'm just going to turn on the output. It claims it is 2.0 volts. This is reading 1.94. Let's see what this meter reads. 1.935. Now I intend to use this supply to charge lithium batteries in the future, so output voltage accuracy is extremely important. Let's see if this accuracy changes once I get up to a different range of voltage. Let's say I want to set it to 3.5 volts. It is actually outputting 3.44. What if I want to go to a much higher voltage? So here we have it set to 60 volts. And it looks like it's pretty accurate at 60 volts. These both read 60. This one is only 0.3 volts off. That's not terrible. If I go to 50 volts, again, pretty accurate. 40 volts, pretty good. 30 volts, not too bad. And there's a few different voltage settings to test the accuracy. It looks like it's about 50 millivolts off from these other two meters at various points. So I'm going to have to keep that in mind for charging batteries, but the accuracy is pretty reasonable. So let's see if we can test the current accuracy of this thing now. I'm just going to set my voltage to 10 volts. Now I have this supply set up to be constant current because my load is simply shorted. I just told my electronic load to short the output, and we can try to turn this current up. Right now it's set to 1.00 amps, and it looks like it's actually outputting 0.98, 0.985. That's very close. Let's just go to 5 amps. That's very, very close. 10 amps. 50 milliamps off, that's not terrible. And let's try the full 20 amps that this unit's rated for. Doesn't appear to regulate all that well. Up at 20 it's only outputting 19.8, but that matches up reasonably well. So for the cost of this unit, I paid about $200 for it. So far everything's checking out okay. So far this AliExpress power supply seems to be doing its job. The output voltage seems to be fairly accurate. The current reading seems to be fairly accurate, and it is capable, at least under a short, of outputting 20 amps. We'll do more testing later, but first I want to open it up and see what's really inside this thing. So it looks like there are a couple of screws on top, and on each side there is 1, 2, 3, 4, 5. So lots of screws here. They're all Phillips heads, so I'm just going to take those all off, take the cover off, and show you what's inside. On the metal-to-metal components, they used machine screws. On the metal-to-plastic, they used some coarse-threaded thread-forming screws. So now I have all of those off, and we'll lift the cover off and see what's inside this thing. See if this really could possibly be a 1200 watt power supply like they advertise. So I'll bring you in for a closer look, but this is the inside of this WANPTech power supply. My first impressions of this power supply are pretty positive. Everything in here seems to be well put together. Everything is extremely clean. The soldering is pretty good. There's a few cold solder joints on here, but nothing too unexpected. It's all put together very well. There isn't any caulking or stabilization for this component here, but the rest of them are pretty good. All of the heat producing components appear to be under this one heat sink. There's a fan here whose brand I don't recognize, a 12 volt fan. That blows directly over it. It's a really nice design that way. 1200 watts, yeah, I think not. But down here we see that there is a thermal protection device. There's a temperature sensor there, so it should shut off if this gets too warm. Here we have the incoming power. It is grounded to the case. They didn't omit the ground. A lot of times they do that on cheap stuff. You have your 2 AC inputs. It goes through a proper filter, common mode choke here, X and Y caps, etc. There's a relay here to connect and disconnect the load. Here we have an inrush protector, an NTC type inrush protector. Over here we have the input capacitor after this bridge rectifier. This bridge rectifier obviously cannot handle the amperage necessary to power the output, so it only powers the power electronics over here. And that's just fine. This capacitor here is a UCC capacitor, or counterfeit, but I'm pretty sure it's UCC. On the output we have UCC capacitors here as well, 105C UCC capacitors, 63 volts. Very, very nice. These chokes look pretty well made to me. Here's the main power transformer for the switching power supply portion of it. I have no idea the quality of this, but it looks just fine. And these are also, I believe, name brand capacitors. These are 400 volt caps for the intermediate PFC boost stage. So overall, I'm pretty happy with the construction of this. There are no-name capacitors over here for a lot of the logic stuff. That's not to be unexpected, so that's not a big deal, but they're 85C, just really cheap stuff. If you look over here at some of these components that are on here, we see name brands. There's one over here that is a Fairchild FET. This flashlight is too bright, I think, for my camera, but there's a Fairchild FET over there. We have an ST IC right here. Another ST IC. Here's a TI IC. Lots of name brand stuff in here. And everything appears to be quite well made. So far, I'm pretty happy with the quality. I did check the tightness of all the screws and such. Everything seemed just fine. Well put together, well assembled. So this front plate here is extremely cheap. It's kind of confusing to me. Why would you put this kind of build quality into the internals and then put this thing on here that makes it look like a Fisher-Price toy? I don't quite understand that. But it does appear to be pretty well made. So far, so good. I think what I'm going to do to stress test this thing is look at the major components that I expect to get warm. And I'm just going to use these two meters. They're both thermocouple meters. Looks like they both agree. They're both reading 21C here where I am. And they are this style thermocouple. I'm going to tape one to this heatsink so that I can monitor how hot the FETs are getting underneath here. And I'm going to tape one to the top of this transformer to see how warm this transformer gets. Those are the two components that I'm most concerned with. We could thermocouple a whole bunch of things up, but I don't want to make this a 3-hour video. So I'm just going to do that, run the cables outside the case, and loosely put the case cover back on so that the airflow is correct. And there's this thermocouple taped onto the bottom of this heatsink, and here taped onto the top of this transformer. And I'll put the cover back on. I was planning to do some load step testing as well as ripple testing, but I think I'm going to omit that here in this video. The most interesting thing to me is to stress test this and see if it can really do the output that it's rated for. So this is a max 200 watt electronic load, 150 volts, 40 amps, but max of 200 watts. So I'm just going to max this out at 10 volts and 20 amps and let it run and see what happens. So we'll set our current to the max here. And then we'll go down here to our electronic load. So we have this set up for 10 volts at 21 amps on our power supply. And I'll set up my electronic load to pull 20 amps at 10 volts and see what happens. There we go, 20 amps. And we'll monitor the temperature of these two meters, one on the transformer, one on the FETs, and see how warm this thing really gets, and if it can really do 20 amps at 10 volts. In the meantime, I want to test and see how accurate the output voltage is under load. So I'm just here behind the unit. I have my multimeter set on DC volts. This is set to 10 volts. And I want to measure at these terminals what the actual output voltage is when there is a 20 amp load. So we're only losing about 50 millivolts to this output under load. So that actually is pretty good in terms of load regulation at the output terminals. Now we are losing quite a bit more voltage if I measure over here, but that loss is in the cables. So even under a pretty high amperage load, the output of this is pretty good in terms of load regulation. A lot of times these power supplies have little thin wires from the output to the circuit board, and you lose a lot of voltage there. This one looks like it's built pretty well that way. Well, this is pretty interesting to me. The fan on this power supply does not run continuously, even at 20 amps and 10 volts. The heatsink warmed up to about 60 degrees Celsius, and then the fan turned on, and now the temperature is dropping. That transformer basically isn't getting warm at all, so that's not very stressed under this 10 volt condition. Maybe it would be at 60 volts. But you can see here that the temperature of this heatsink that the fan is blowing over is dropping, as you would expect when a fan blows over it. So this power supply is absolutely no problem whatsoever at 10 volts and 20 amps. So I think I will stop the test here because it simply isn't getting any warmer. Now this isn't meant to be a full review of this power supply. I'm just testing this power supply out for my own purposes here. So that's why I decided not to grab my oscilloscope and take a look at the ripple and such. My intended use case of this is to charge batteries. Lithium batteries at 3 point whatever volts, and lead acid batteries at up to 60 volts, because you need 60 volts to charge a 48 volt battery bank properly, and for inverter testing. So why not just test it out that way? This is a reliable electric 4000 watt inverter. And this can do a lot more than the 200 watts of my electronic load, so I'm going to use this as a higher wattage electronic load to see what this thing can really do, because I highly doubt it can do 60 volts and 20 amps at the same time. That's 1200 watts. Seems unlikely. I'm thinking it'll max out at maybe 500 watts or so. But we'll find out. And for a load on this 4000 watt pure sine wave reliable electric inverter, I'm just going to use that heater over there. It has two settings. One is 400 watts, one is 800 watts. So let's power these things on and see how it works. Now this power supply does have a memory So it remembers the setting that it was on last time, which is nice. And this is a 48 volt inverter, so I'm going to set my voltage to, we'll just set it to 52 volts. Set it to 50, that makes for easy calculations. And these two are connected up already. So 50 volts, 21 amps. I should be able to turn this on and get an output. Oh yeah, I suppose I have to turn this on, don't I? That would be good. Alright, now I should be able to turn it on. And it looks like it is overloading this power supply. That's pretty common. The input surge on these is really high, and it frequently overloads it. So what's going on is this inverter is going into like a pulse skip mode. It's charging the capacitors inside, and because the load is so small, it is overcharging the caps. It shuts down, waits for the caps to drain down, and then tries to charge them again. Each time it does this, there's a very large current pulse that happens, and this power supply doesn't respond fast enough to that current pulse. So it is not adequately powering it for that reason. So what we can do to get around this problem of the current surge, this power supply not being able to handle that surge when it charges up those caps, is to simply back this voltage down so those caps never overcharge. This is pretty common on lab style power supplies just because the input capacitance of a 4000 watt inverter is an order of magnitude larger than any lab power supply. So I'm not really going to blame this power supply for that. This is simply inadequate to power a load this large. If I had a 500 watt inverter, it would probably match up better. So I'm going to turn this down, and I believe we'll see that this light will end up steady. And now we're getting nice solid power out of it. So now I'm going to go to my heater and turn it on 400 watt low. And now that heater is on, I believe I'll be able to turn this voltage up. Let's see if I can. There we go. 50 volts. So I think I'm just going to let this run for a while. Well, it just blew up. Okay. Well, apparently it did not like that very much. Let's take that cover off and see if we can see if there's anything wrong with it. I heard and saw the pop. Oh, it's just my output terminal here. I'll show you what's going on. These ring terminals didn't really fit very well, and this got loose. So that is completely my fault. Let's see if I can get a better setup than this, because this is not very good. I decided to be super lazy. I just tightened it back down again. Let's plug this thing in and see if it works. It did work for our 20 amp load before. There's no reason why it shouldn't work here. Hopefully it doesn't come loose again. And the heater is on. So hopefully it will stay running this time. 50 volts times, we'll just say 9 amps. That is 450 watts. It's a 400 watt heater. This inverter isn't 100% efficient. So we will just let this run. We'll see if this thing can handle it. In the meantime, I'm going to turn this heater away because I don't want that to warm up everything here. Put this on temperature. We got a little something going on here. Well, I'm running into a little bit of a problem with this meter. I don't know what's going on with it. I can't imagine why a meter I got for free from Harbor Freight wouldn't work, but for some reason it's not. So I'm just going to be swapping the thermocouple into this particular meter. I do have a dual thermocouple scientific meter, but I haven't actually tested these leads with it. I don't have an adapter to go from a standard thermocouple lead to these, so I'm just using this. But this is connected right now to the heatsink of here instead of the transformer. I can swap it over to the transformer, which goes here, at any time. So we'll just let this run, and I assume that this temperature will do what it did before, go up to about 60 Celsius, and then the fan will turn on. And we'll see if the fan turns off again, if it can actually cool it off enough to turn it off. And there the fan is turned on. Apparently it's at about 50 Celsius, not 60 like I had said. And we'll see if the temperature cools off and the fan shuts off again. Looks like the temperature is slowly falling. It was rising, of course, as it ran with no fan. Now it's falling. And once it falls far enough, then the fan should shut off. And there we go, the fan shut off. So this is very capable of doing 450 watts. Let's see if I turn my heater here onto high, which is 800 watts. I switched the thermocouple over to the transformer. Apparently I had no reason to worry about the transformer. The temperature is still pretty low, and if it is rising, it's rising pretty slowly. I'm sure it'll creep up over time, but obviously that thing's not going to get that hot. The only real heat I can feel coming out of here is right here. This vent over here is cool. If I go further to back, this one is warm. So one of those chokes that's in this side of the power supply over here must be getting quite hot, but I'm not too worried about those chokes. That should be fine. It's the transformer and all those FETs that I'm most worried about. There's a whole bunch of other little components in there that might be getting hot if it's designed poorly, but it seems to be designed pretty well. This fan is running constantly now in here. Looks like this is still creeping up very slowly, but considering this can get much warmer before it's a problem, I think I will just ignore that transformer from now on. Apparently that's not an issue. And we'll plug back in the heatsink temperature. And it is hanging right at 50°C. Looks like it even cooled off a couple of degrees while this fan ran. At 850 watts. So this power supply looks like it can do exactly what I need. It can do 20 amps at any voltage up to at least 50 volts, probably higher. Seems reasonably accurate. The smoothness on the output and such, I'm not really sure, but it's probably going to be just fine. There's a lot of caps in this thing, so it should be relatively smooth. There are a few things that I don't really like about it. It feels really cheap. This front panel's cheap. I bet it will yellow pretty quickly. It's already a little bit yellowed. That's common with cheap plastics. And there's something going on here with this display flickering. I don't know if you have caught that on camera, but every once in a while the display flickers. I'm not sure what is going on when it's doing that, if the output voltage is stable or not, but this inverter at least doesn't seem to care. And it seems like the voltage defaults back to tenths of a volt every time. See here it's at tenths of a volt. If I hit it here, now we're adjusting by 1 volt. But if I let it time out here, and now I want to adjust the voltage again, if I go back here and adjust it, of course now it works. Every other time it went back to a tenth of a volt. So it seems to reset every once in a while. And that's the inverter fan that just turned on there. See, now it went back to a tenth of a volt. I'm kind of wondering if every time this display flickers that the logic resets or something. Something is not quite right in there. Yeah, so it's a tenth of a volt now. Will it flicker if I'm adjusting this? I'm just going to wait for it to flicker here and see if that's what's triggering this reset back to a tenth. No, that is not what's doing it. It must be a timeout. If I let it sit long enough, it times out and goes back to tenths of a volt. Anyway, that's kind of annoying to me, but I'm guessing they do that because if you're doing it by tens of volts and you forget and then start turning the knob, that you could blow something up. So I'm guessing that's why they do that. Yep, it went back. But anyway, this little power supply here seems like it's a reasonable value. I picked it up for, I think it was $200, which is pretty good for a 60 volt, 20 amp lab style power supply, and it does seem to function. So I got this on AliExpress. I'm not sure where else you can get it, but I'm reasonably happy with it. So that's going to end this video. I just wanted to mess around with this power supply, make sure it worked for my needs. I only have a few days to return it if it doesn't work, and I'm going to keep it. So this is Neural, thanks for watching. One last thing here, I thought it would be good to show the power factor of this power supply, just to see if it's terrible or good. After all, 1200 watts is quite a bit, and if you're running it on a 15 amp circuit, the current draw might become pretty important. It doesn't generate a lot of heat, so obviously it's fairly efficient. I have my heater on the floor. That is just a 400, 800 watt heater, and it's hooked up to the inverter. There's 400 watts. And the input voltage is 120 volts, 6 amps, for a power factor of 0.7. It's not terrible, but not great. Let's turn this heater up to 800 watts. Power factor is still about 0.7, drawing 11.5 amps from the wall, 119 volts, a little bit of drop in my extension cord. So this is not power factor corrected. That is certainly no surprise whatsoever, but just something to note.